For 300 years, physicists have been quietly hoping that nature would refuse to build one particular object. The object is the singularity, a point of infinite density at the heart of every black hole, where the equations of general relativity stop producing numbers and start producing infinities. Every generation since 1783 has searched for a rescue. Every generation has been wrong. The horizon forms, the collapse continues, the matter falls all the way down. But in 2014, a quiet proposal emerged from a small program inside theoretical physics that at the deepest possible scale, 16 orders of magnitude beyond anything the Large Hadron Collider can probe, the grain of spacetime itself pushes back. The collapse halts. A trillionth of a meter-wide ball of frozen Big Bang density energy forms inside every black hole that has ever existed. 40 million of them in this galaxy alone, held in place, motionless, by gravity so extreme that the rest of the universe will live and die before the bounce is even finished. If this is right, what is at the center of every black hole in the visible cosmos? And what does that mean for what the universe actually is? Get comfortable, subscribe if you have not, and stick around, because the picture we are about to walk through quietly turns 3 centuries of hope inside out. Let us get into it. Part 1. The Hope. For 300 years, physicists have been quietly hoping that nature would save them from one specific object. They have been hoping that somewhere in the math, at some scale they had not yet probed, in some quiet corner of the equations, a piece of physics would arrive at the last possible moment and refuse to let one particular thing exist. They have been hoping that the universe, having been built carefully enough to permit galaxies and starlight and atoms that hold themselves together long enough for life to look up and ask questions, would not, in the end, also permit the worst object the math can describe. They have been hoping for a rescue. The object they have been hoping to be rescued from is the singularity, a point of infinite density, a region where space and time fold in on themselves so completely that the equations describing them stop producing numbers and start producing infinities. A place where the deepest theory of gravity we have, general relativity, looks at its own predictions and refuses to say what happens next. The singularity is the place where physics breaks. And for 3 centuries, the people whose job it is to describe the universe in equations have been quietly, persistently, almost embarrassingly hopeful that nature would never actually build one. What you have to understand about this hope is how old it is and how stubborn. Every generation of physicists since the late 1700s has watched the math force ultimate gravitational collapse, and every generation has been saved at the last second by a piece of physics nobody had seen coming. A new law would appear, a new quantum effect, a new pressure pushing back. The collapse would halt, the equations would stabilize, and a room full of relieved physicists would write a paper explaining that the universe had, once again, refused to build the absurd object. And then, 50 years later, the math would catch up. Someone younger would extend the equation past the new rescue. They would prove the rescue had a mass limit, a place where it failed and the collapse resumed. The older physicists, the ones who had built their careers on the rescue, would have to watch a new generation tell them that the universe was, in the end, allowed to build the thing. The cycle would repeat. We are still inside this cycle. We are still hoping. We have just gotten very, very close to the bottom of the staircase. Tonight we're going to walk through that cycle, one rescue at a time, from the very first guess of the late 1700s, all the way through to a proposal from 2014 and an update from 2024 that may, finally, be the rescue the discipline has been waiting for. Or may equally not be. We're going to follow the math through 300 years of failed rescues against gravitational collapse, and we're going to arrive, at the end of that journey, at the strangest object physics has ever proposed. An object the size of 1/10,000th of a hydrogen atom, sitting at the heart of every black hole in the visible universe. an object held there, motionless, for 10 to the 64th years, by gravity so extreme that time itself has stopped inside it. An object that is, if the math is right, a sealed fossil of the moment the universe began. A fragment of the Big Bang. Preserved. Forever. Inside something we used to think was the end of physics, and which may turn out to be instead the place where the beginning is hidden. The object is called a Planck star, and before we get to it, before we earn the right to look at it directly, we have to walk the staircase. Because the Planck star is not an answer that arrives out of nowhere. It is the answer that arrives at the end of 3 centuries of asking the same question and being wrong. So let us begin at the top of the staircase where the question first appeared in a country parsonage in 1783, when an English clergyman wrote down a letter that contained, almost by accident, the first description of a black hole. His name was John Michell, and he had no idea what he had done. He thought he was just doing a thought experiment. He thought he was just exploring a mathematical curiosity about what would happen if you made a star large enough that its escape velocity exceeded the speed of light. He was working in Newtonian gravity, which was the only gravity anyone had in 1783, and in Newtonian gravity, light was understood to be a stream of particles which felt gravity the way any other particle would. So Michel asked a simple question. How large would a star have to be before its own gravity prevented its own light from leaving its surface? And he did the arithmetic. And the answer was about 500 times the size of the Sun. A dark star. An object so massive that it was, in principle, invisible. Not because it gave off no light, but because the light it gave off could not get out. Light would leave the surface, slow down under gravity the way a thrown rock slows down, run out of speed, and fall back. The star would shine, internally, forever, and the universe outside it would see nothing. This was the first time anyone in history wrote down an object that swallowed light. And what is interesting about Michel and his French counterpart Laplace, who arrived at the same idea independently in 1796, is that they were not alarmed. They were not horrified. They were not sounding any kind of warning. They thought it was a curious mathematical artifact. They thought it was the kind of thing that, with a little more thought, would turn out to be impossible. That some natural process would prevent a star of 500 solar masses from ever assembling in the first place. And so the dark star would remain a thought experiment, a mathematical exercise, a small curiosity at the bottom of a longer paper about stellar parallax. The hope, even in 1783, was already there. The first time anyone wrote down the math of a black hole, they wrote it down with the quiet expectation that the universe would have the good sense not to actually build one. And for a while, it looked like the universe agreed. Because Michel was right, as it turned out, about the impossibility of his particular dark star. You cannot, in fact, simply assemble a 500 solar mass cold object out of dust and gas. Giant clouds of gas do not collapse smoothly into one enormous body. They fragment. They break up into smaller clumps. They form thousands of smaller stars instead of one impossible giant. The Newtonian dark star, as Michel had described it, cannot form in nature. The first dark star rescue was the rescue of stellar formation itself. The universe, it seemed, had built a process that prevented matter from collecting into the kind of body Michel had imagined. The first hope, in this very narrow sense, was justified. The first generation of physicists, if we want to count Michel as a physicist, were saved. But here is the thing that the first rescue did not save us from. Every collapsing fragment of that giant cloud, every smaller piece of gas that breaks off and starts to fall in on itself under its own weight, is, itself, a candidate for the same problem. Every collapsing cloud is, in miniature, the same gravitational situation that Michel was worried about. Every one of them is a body falling inward on itself. Every one of them, if nothing intervenes, will eventually arrive at the same place. The Newtonian dark star was prevented. But the underlying problem, the tendency of mass to collapse on itself, given enough of it in a small enough region, was not prevented. The first rescue saved us from a specific monster, while quietly building in the same act a million smaller candidates for the same monster. This is the pattern. You will see this pattern repeat. Every rescue solves the immediate problem and quietly, almost mockingly, sets up the next one. The discipline gets saved from the dark star, and the saviour is the messiness of stellar formation. But stellar formation is what produces stars, and stars, in the end, are exactly the bodies that produce black holes. The rescue is the seed of the next failure. The reprieve contains, inside itself, the next collapse. This is the underlying rhythm of the story we're about to walk through, and it is worth holding in mind because the rhythm will not break until very, very late in the journey. Until perhaps an idea published in 2014 finally turns out to be the rescue that does not, quietly, contain the seed of its own failure. And then, when we get there, you will see that even that rescue, even the Planck star, which is the rescue this entire video is named for, may not in the end be a rescue at all. It may be something else. It may be a preservation, which is a different word with a different meaning, and we will come back to that word at the end. But for now, for this first chapter, hold on to the pattern. 300 years of physicists hoping the universe would refuse to build the worst object the math can describe. 300 years of clever rescues, each of which turns out to contain, inside itself, the seed of the next failure. And sitting at the end of all of this, an object we are going to spend the rest of the night describing in increasing detail. An object that may finally be the answer. An object that may, equally, just be the latest rescue we are still hoping is right. An object whose interior is 1 trillion times larger than the shell that supposedly contains it. An object that is, if the math holds, a sealed fragment of the first instant of the universe, preserved inside the heart of every black hole, frozen there by gravity so extreme that the rest of the cosmos will live and die before that one fragment of beginning has even noticed it has rebounded. An object older than time, in the only sense of older that matters, sitting motionless in the dark. That is where we're going. But first, the staircase. First, the rescues. First, the long slow walk down to the place where, after 3 centuries of asking the same question, and being wrong, we finally arrive at the place where the math might this time be telling us something true. Let us begin the descent. Part 2. Dark Stars. Let us return to John Michel, because there is more to say about him, and about what he actually wrote down, and about why his particular monster was the easy one to dispatch. Michel was a rector, a country clergyman in the village of Thornhill in Yorkshire, England, with a side interest in natural philosophy that today we would call physics. He had already done first-rate work on the inverse square law of magnetism. He had invented the torsion balance that Henry Cavendish would later use, after Michel's death, to weigh the Earth. He was one of the most underrated minds of his century, and in 1783 he wrote a paper that was read aloud to the Royal Society and then almost entirely forgotten for the next 200 years. The paper was a long, careful, almost meditative argument about how one might measure the masses of stars by observing how their light slowed down as it climbed out of their gravitational fields. It was a paper about how to do astronomy, not a paper about end-state cosmology. But at the very end of it, almost as an afterthought, Michel did a small calculation. He asked, suppose a star were so massive and so dense that the escape velocity at its surface exceeded the speed of light. What would such a star look like? And the answer he gave was the first description of what we now, 2.5 centuries later, call a black hole. He called them dark stars. He thought there might be many of them in the universe. He thought, somewhat charmingly, that we might be able to detect them indirectly by watching luminous companion stars in binary orbits with invisible massive partners. He was, in this last respect, exactly right, and he was about 200 years ahead of his time. The first confirmed stellar mass black hole, Cygnus X1, was found in 1971 in exactly the way he had predicted, as the invisible massive partner of a luminous companion. Michel had imagined the detection method before the existence of the object he was looking for was widely accepted. But the dark star Michel described was, in detail, not a black hole. It was a Newtonian dark star. It was an object whose gravity was strong enough, in Newton's framework, to drag light back to its surface. It was an object that, in Newtonian terms, was made of ordinary matter held together against its own immense weight by ordinary material strength. It was, in his imagination, something close to a very dense planet. And Michel thought such an object might be about 500 times the diameter of the Sun, because at that diameter, at the density of the Sun, the escape velocity at the surface would equal the speed of light. Anything larger, and light could not escape. Anything smaller, and it could. The number 500 is the canonical number, the one Michel himself worked out and wrote down, and the one that has been quoted in every history of the subject ever since. What we now know is that this object cannot form. The chain of physics that takes you from a giant cloud of interstellar gas to a single dense object of 500 solar masses is broken at almost every step. Giant gas clouds do not collapse smoothly. They fragment under their own gravity into smaller pieces. The smaller pieces collapse into stars. The stars ignite. The ignited stars push back, with radiation, with stellar wind, with the sheer pressure of light leaving their surfaces, and they push back hard enough to disrupt any further accumulation of mass on top of them. By the time a star is more than around 150 solar masses, the radiation pressure is so violent that the star tears its own outer layers apart. It cannot accumulate more mass. The famous Eddington limit, named for Arthur Eddington, who we will meet in the next chapter, is the formal expression of this. Above a certain mass, a luminous body cannot accumulate further matter from its surroundings. The matter is pushed away faster than gravity can pull it in. The 500 solar mass Michel dark star is, in modern astrophysics, simply not allowed. It cannot be built. The factories do not exist. So Michel's monster, in the form he described it, was prevented by nature. Not by any deep new physics, but by a fairly mundane fact of how gas clouds collapse, and how massive stars push back on their own surroundings. The rescue in this case was simply the messiness of stellar formation. Nature did not need to invent any new law. It just had to be a little disorganized. The disorganization saved us, and here, already, we encounter the pattern I warned you about in the first part. Because the rescue from Michel's dark star was, at the same time, the construction of all the smaller objects that would, in the end, produce the actual black holes that exist in the universe. The fragmentation that prevented the dark star is the same process that builds the dense star clusters in which black holes are made. The radiation pressure that prevented further accumulation onto a giant star is the same pressure that, when the star eventually runs out of fuel, vanishes, allowing the collapse to resume. The rescue did not eliminate the problem, it postponed it. It scattered it into 1 million smaller candidates. Each of those candidates would, in due time, get its own turn at trying to collapse to a point. There is something almost poignant about Michel's mistake. He thought he was describing an object that nature might just barely allow. He did not realize that nature was not going to build his particular object, but that it was going to build, in enormous numbers, the family of smaller objects that would do the same thing. Our own Milky Way contains, by current estimates, something on the order of 40 million stellar mass black holes. They are not 500 times the size of the Sun. They are the size of a small city. But they do exactly what Michel was worried about, and there are 40 million of them in this one galaxy. For about a century after Michel and Laplace, the dark star concept sat quietly in the literature, half forgotten. Wave theories of light pushed the particle picture out of fashion. The question simply stopped being asked. It would have to wait for Einstein, and for Karl Schwarzschild, working on the Eastern Front of the First World War in 1915 and 16, while dying of a skin disease, to derive the radius that would bring the dark star back, this time as a real geometric feature of general relativity itself. But that is a story for a few chapters from now. For now, Hold the picture of Michel at his desk in Yorkshire in 1783, the candle low, the ink pot near. Hold the picture of a country clergyman with a side interest in physics, doing the arithmetic of escape velocity for the largest possible stars, and writing down, for the first time in human history, the existence of an object that swallowed light. Hold the picture of him being calm about it. Hold the picture of him assuming, as everyone assumed for the next 200 years, that this was a curiosity, that nature would prevent it, that the rescue would come, and then notice again the pattern. Michel's specific monster, the 500 solar mass cold dark star, held together by Newtonian gravity and the material strength of dense matter, was prevented. Not by a piece of new physics, but by the disorganization of stellar formation. The rescue, in 1783 terms, was real. But the rescue contained the seed of the problem. The fragmentation that prevented the dark star produced the stars that would, in the next chapter, themselves become candidates for the same collapse. Each of those candidates would, in turn, be saved by a new rescue. Each new rescue would have, hidden inside it, the seed of its own next failure. We are still walking. We have descended one step. The dark star is behind us, prevented by the messiness of how gas becomes stars. But the stars, the actual stars that get built instead, are themselves about to become candidates for the same problem. They will burn for a few million or a few billion years, and then they will run out of fuel, and the rescue that kept them stable, the rescue we are about to discuss in the next chapter, will fail, and the collapse will resume. And the question of what stops it this time will have to be answered by an entirely different piece of physics, a piece that did not exist in 1783, a piece that would arrive only in the 1920s, only after quantum mechanics was invented, and only after Arthur Eddington had spent a decade working out exactly how a star, against all odds and against all weight, manages to push back against its own gravity and shine. Let us go to Eddington, let us go to the second rescue, let us go to fusion. Part 3. The Sun's Refusal. In the early 1920s, an English astrophysicist named Arthur Stanley Eddington stood at a chalkboard at Cambridge and tried to answer a question that had not, until then, been properly asked. A star is a body held together by its own gravity. The pressure at the core of the Sun, by every reasonable calculation, ought to be crushing the matter there. The matter at the centre of the Sun should be falling inward. The Sun should be collapsing. And yet, by every astronomical accounting, the Sun has been holding for billions of years. Something is pushing back. The question was, what? Eddington had a guess. In 1920, he wrote down the first serious version of the guess in a paper to the British Association for the Advancement of Science titled The Internal Constitution of the Stars. His guess was that the energy holding the Sun open against its own gravity was somehow the conversion of hydrogen into helium in the deep interior. The arithmetic of this was suggestive but not yet rigorous. The actual mechanism by which one element transforms into another was, in 1920, not known. Nuclear physics had barely been invented. The neutron had not yet been discovered. Quantum mechanics was a few years away from existing in its modern form. Eddington was essentially guessing, but he was guessing with such clarity and such physical intuition that his guess turned out, in detail, to be right. Hydrogen in the core of a star is fused into helium. The mass difference between the input and the output is released as energy, in the form of high-energy photons that batter their way outward through the body of the star and eventually emerge from its surface as sunlight. The energy released in this process pushes outward, against gravity. The outward push and the inward pull balance, exactly, for as long as the star has fuel. The star holds. What this means, and what Eddington in his quieter moments must have understood, is that every star is, in a precise mechanical sense, a delayed black hole. A star is a body that has been falling inward under its own gravity from the moment of its birth, and has only stopped falling because, at a certain critical density and temperature in its core, the nuclear physics ignites, and the resulting outflow of energy holds the rest of the body open. The collapse is paused, not stopped, not prevented, paused. The clock on the collapse is still running. It is just running at a rate determined by how much nuclear fuel the star has and how fast it is burning it. When the fuel runs out, when the last hydrogen is fused, when the helium itself begins to burn, when each successive element in the chain produces less energy than the one before it, the pause will end. The collapse will resume. And what was for a few billion years a stable shining star will become, in a single act of inward fall, exactly the kind of object Michel had been worried about. This is what is quietly horrifying about a star when you understand the physics. The warm yellow body that makes life possible on this planet is, in its deep mechanics, a body in mid-fall. The sun is, right now, falling inward. It has been falling inward for 4.5 billion years. The fall is so perfectly counteracted by the outward push of fusion that we cannot see it. But the fall is real, and it is constant. The sun is not a permanent feature of the cosmos. The sun is a temporarily delayed collapse. In about 5 billion years, the fuel will run out, the pause will be over, the collapse will resume. This was the second rescue. This was the rescue Eddington had identified, and that the nuclear physicists of the 1930s, Beth, Weizsäcker, Critchfield and others, would complete by the end of that decade. The rescue was real. The rescue was not magic. The rescue was simply the fact that a sufficiently hot, sufficiently dense core of hydrogen would, under the new rules of quantum mechanics, undergo nuclear fusion, and the resulting outflow of energy would, by a margin of stunning precision, exactly balance the inward gravitational crush. A star is a body in balance, held there by the most powerful continuous nuclear reaction in the visible universe. The reaction has been running in our Sun for 4.5 billion years. It will continue to run for about 5 billion more, and then it will stop. When it stops, the star does not simply die in place, it dies in stages. First, the hydrogen at the core runs out, and the core contracts, and the contraction heats it further, and eventually the helium that has been accumulating in the core ignites, and a new round of fusion begins. The star puffs up into a red giant. The outer layers expand and cool. The core contracts. New elements are forged. Helium becomes carbon, oxygen, neon, magnesium, silicon, all the way up to iron, in a precisely ordered sequence of nuclear reactions, each one shorter than the last, each one producing less energy than the last. Iron is the dead end. Iron, in the chain of nuclear fusion, gives back no energy when you fuse it further. So when the core of a sufficiently massive star reaches iron, there is no more rescue available. The fusion stops, the outward push vanishes, the gravitational crush, which has been there all along waiting, finally has nothing to push against. And so the core falls. It falls in seconds. It falls in a way that has no analogue in human experience, because the mass of the entire core, comparable to the mass of the sun, falls inward at significant fractions of the speed of light. The outer layers of the star, which were being held up by the radiation pressure of the core, suddenly have nothing beneath them, and they fall too, and they slam into the collapsing core, and they rebound, and they explode outward as a supernova. The sun's refusal, the rescue we have been discussing, ends in catastrophe. But the catastrophe is not by itself what we are here to discuss. The catastrophe is well understood. The catastrophe is the visible event, the supernova, the bright point of light visible across a galaxy, the cosmic event that delivers most of the heavy elements in the universe to the interstellar medium. The catastrophe is the part of the story that astronomers have been observing for centuries. What we're here to discuss is what happens after the catastrophe. What we're here to discuss is the question of what the collapsing core, the part that did not explode outward, but instead continued to fall, finally becomes. If the original star was massive enough, somewhere between about 10 and 25 times the mass of the sun, the collapsing core is too heavy for any of the next two rescues to save it. It will fall through every available pause. It will not be caught by electron degeneracy pressure, which would have saved a smaller core. It will not be caught by neutron degeneracy pressure, which would have saved a slightly larger but still bounded core. It will pass through both. It will keep falling, and at the end it will form an event horizon, and it will become a black hole, and we will lose the rescue for the last time. But we're getting ahead of ourselves. The order of operations matters. The order is what makes the story make sense. Because each of the next two rescues, electron degeneracy and neutron degeneracy, was hoped, in turn, to be the final answer. Each of them was, in turn, believed for a generation. Each of them was, in turn, broken by a younger physicist who pushed the equations one step further. The first of those two rescues, the white dwarf, is the rescue of the smaller dying stars. It is the rescue that catches the sun. When the sun finishes burning its fuel, 5 billion years from now, give or take, it will not become a black hole. It will not be massive enough. It will pass through the red giant phase, shed its outer layers as a planetary nebula, and the remaining core will settle into a tiny, dense, slowly cooling object about the size of the Earth, held up against its own gravity by a piece of physics so strange that it does not arrive at all until quantum mechanics is invented. The sun will end as a white dwarf. The sun, in this sense, gets caught. The rescue holds for our particular star. For a while, in the 1920s, it looked like the rescue would hold for every star. For a while, the discipline thought, finally, that the search for the rescue was over. It was not. We are about to walk into the chapter where a 19-year-old on a steamer from India to Cambridge sat down with a sheet of paper and proved, in the long, slow voyage across the Indian Ocean, that the rescue physicists had just discovered had a failure point, and that for any star sufficiently massive, for any white dwarf 40% heavier than the Sun, the rescue would, in turn, fail. The rescue was almost what they had hoped for. The rescue was very nearly the answer, but it was not the answer, and the person who proved it was not the person who had discovered the rescue. The person who proved it was a young man, dressed in starched whites, on the deck of a ship, drinking tea and watching the equator pass beneath him. His name was Subramanian Chandrasekhar. He was on his way to Cambridge to study with Ralph Fowler, the physicist who had just published the white dwarf result. He was 19 years old. He had a copy of Eddington's textbook in his cabin, and by the time the ship arrived in Southampton, he had worked out in private the calculation that would tell the discipline that the rescue they had just celebrated was again going to fail. Let us go to Chandrasekhar. Part 4. The White Dwarf and the Voyage to Cambridge. In 1926, a young English physicist named Ralph Fowler published a short paper in the monthly notices of the Royal Astronomical Society. The title was modest. The paper was 8 pages long. The paper was, in retrospect, one of the most consequential papers in the history of astrophysics. It was titled On Dense Matter, and what it did was take the new quantum mechanics, barely a year old in its mature form, just published by Heisenberg and by Schrödinger, just being absorbed by the rest of the discipline, and apply it for the first time to the question of what happens to a star at the end of its life. The argument Fowler made was this: when a star runs out of fuel and the core finally begins to collapse, the electrons in the core are pushed closer and closer together. There is a rule in the new quantum mechanics, called the Pauli exclusion principle, which says that no two electrons can occupy the same quantum state at the same time. There are only so many slots available. As the electrons get compressed, they have to fill higher and higher energy states, and the higher states require the electrons to move faster, and the faster electrons push back. They push back not because of any temperature, not because of any thermal motion, not because of any classical pressure, but simply because the quantum rules forbid them from doing anything else. The electrons cannot occupy already filled states. They are pushed up the energy ladder, and the energy of their motion creates a pressure outward, and that pressure can hold against gravity. The pressure is called electron degeneracy pressure, and it has the strange property that it does not depend on temperature. It is a pure quantum effect. It would work in principle even at absolute zero. Even in a body so cold that no thermal motion was happening at all, the electrons would still be moving, would still have to be moving, because the quantum rules forbid them from being still. Fowler showed that this pressure was enough to support a collapsed stellar core against further gravitational collapse. The body would settle into a stable configuration about the size of the Earth, but containing the entire mass of a star. The density would be on the order of 1,000,000 grams per cubic centimetre. A single teaspoon of the material would weigh about 15 tons on Earth. This was the white dwarf. The name had been used before by Adrian van Manen and others for the faint, hot, dense objects that had been observed since around 1890. But Fowler was the first person to explain, from first principles, why such an object existed and why it was stable. The rescue had arrived. Quantum mechanics, barely off the press, had just stepped in and saved physics from gravitational collapse. You have to imagine what this felt like in the 1920s to understand why the next chapter was so emotionally fraught. For 2 centuries since Michel, the discipline had been quietly anxious about what stops gravitational collapse. The Michel dark star had been a curiosity, forgotten, then revived after Schwarzschild's solution to Einstein's equations in 1915 made the question pressing again. The discipline had been waiting for a rescue. Eddington had identified the rescue for the stable phase of stellar life. Fusion held the star open while it had fuel. But the fuel would eventually run out, and the question of what happened then had been the central unanswered question of stellar astrophysics for almost a decade. And then, in 8 pages, Fowler answered it. The white dwarf was the rescue. The white dwarf was the end of the story. It was not. In the summer of 1930, a 19-year-old Indian physics student named Subramanian Chandrasekhar boarded a ship in Bombay bound for Southampton. He was on his way to Cambridge, where he had been accepted to do graduate work with Ralph Fowler, the same Ralph Fowler who had just, 4 years earlier, identified the white dwarf as the rescue. Chandrasekhar had Fowler's paper in his cabin. He had Eddington's textbook in his cabin. He had been raised in Madras in a Tamil Brahmin family of formidable scientific accomplishment. His uncle, Chandrasekhara Venkataraman, would win the Nobel Prize in Physics that same year for the discovery of what is now called Raman scattering. The young Chandrasekhar was widely expected by his family and by his teachers to also win a Nobel Prize. He would. It would take him 53 years. He was 19. The voyage from Bombay to Southampton took 18 days. He had a notebook, a pen, an inkwell, and in private, a question. The question was this. Fowler's calculation of the white dwarf assumed that the electrons in the collapsed core were moving slowly compared to the speed of light. That assumption was reasonable for low-mass white dwarfs, where the densities were modest. But what about for high-mass white dwarfs? What about for a white dwarf containing a mass larger than the Sun? At those higher masses, the electrons would be packed so tightly that the energy levels they would have to fill would be relativistic. The electrons would be moving at significant fractions of the speed of light. And in that regime, the equation for degeneracy pressure changes. The pressure no longer rises as fast, with increasing density, as it did at lower densities. In the relativistic regime, the pressure rises more slowly, and gravity, of course, does not care about relativity in this sense. Gravity keeps pulling at the same rate. So there is a question. Does the pressure in the relativistic regime rise fast enough to keep up with gravity? Or does gravity at some point win? Chandrasekhar did the calculation in his cabin. He did it on the deck. He did it in the dining room. He did it for 18 days. And by the time the ship reached Southampton, he had the answer. And the answer was, gravity wins. For any white dwarf above a certain mass, a mass that he calculated in the original paper to be about 1.25 solar masses, and which we now know more precisely to be about 1.4 solar masses, the relativistic degeneracy pressure cannot keep up with gravity. The white dwarf becomes unstable. It cannot exist in equilibrium. It cannot in fact be a white dwarf at all. It will collapse. This number, 1.4 solar masses, or about 40% more than the mass of the Sun, is now called the Chandrasekhar limit. Above it, the rescue fails. The collapse resumes. The question of what stops it in that case is once again open. A 19-year-old, on a ship in private, had just proved that the rescue physicists had been celebrating for 4 years was not enough. He arrived in Cambridge. He showed his calculation to Fowler. Fowler was generous and intrigued and helped him publish it in the Philosophical Magazine in 1931 and in a more developed form in the monthly notices of the Royal Astronomical Society in 1935. Chandrasekhar spent 5 years polishing the calculation, working out the detailed structure of relativistic degenerate matter, working out what would happen to a white dwarf as it approached the limit from below. He was meticulous. He was correct. And on the 11th of January 1935 he stood up at a meeting of the Royal Astronomical Society in London, presented his result, and was publicly humiliated. Emotional anchor, Eddington's refusal. The humiliation came from Arthur Eddington, the same Eddington who had worked out fusion as the rescue that holds a star open, the same Eddington who was the most distinguished astrophysicist in Britain, and who had been Chandrasekhar's mentor and dinner guest for the previous 4 years. Eddington rose immediately after Chandrasekhar's talk. He told the assembled Royal Astronomical Society that the result was, in his words, almost a reductio ad absurdum of the relativistic degeneracy formula. He suggested the formula itself must be wrong, because the consequence, that nature would permit ultimate gravitational collapse, was unphysical. He said, in essence, that the rescue must hold because the alternative was unacceptable. He said this with great authority in front of the entire British astrophysics community to a 24-year-old who had spent 5 years carefully and correctly working out the math. The audience believed Eddington. For about 3 decades, the consensus in the British astronomical community was that Chandrasekhar must be wrong. The discipline could not accept the conclusion that nature permitted ultimate gravitational collapse. The hope for a rescue was too deeply embedded. The need to believe that some piece of physics would step in at the last moment was too strong. Eddington was Eddington. He had spoken. The question, for the British community at least, was closed. It was not. The American community took Chandrasekhar more seriously. The Russian community took him more seriously. The young physicists everywhere, those without the emotional investment in the rescue, took him more seriously. And by the late 1930s, when the careful nuclear physics community had checked his calculation independently, the answer was no longer in dispute. Chandrasekhar was right. Eddington was wrong. The Chandrasekhar limit is real. Above 1.4 solar masses, the electron degeneracy rescue fails. But the damage was done in Chandrasekhar's life, if not in the physics. He left Cambridge in 1937, partly because the relationship with Eddington was beyond repair, and took a position at the University of Chicago. He stayed there for the rest of his career. He did vast and various and beautiful work on stellar structure, on radiative transfer, on the dynamics of star systems, on the mathematical theory of black holes themselves. He won the Nobel Prize in 1983, almost 53 years after his 18 days on the ship from Bombay. He was 83 when he won it. He died in Chicago in 1995. The lesson of this chapter, for our purposes, is not just that Chandrasekhar was right and Eddington was wrong. The lesson is that the hope for a rescue is itself a powerful force in physics. The discipline does not, at every moment, follow the math. The discipline has emotional investments. The discipline has senior figures who do not want to abandon the picture they have built their careers on. The hope that nature would, in the end, refuse to build the worst object the math can describe is so deeply embedded that even Arthur Eddington, one of the finest astrophysicists of his generation, one of the deepest readers of general relativity, one of the founders of the modern theory of stellar structure, could not, when confronted with a young man with a correct calculation, accept that the rescue was not coming. We have just walked down another step on the staircase. The white dwarf, the second rescue, has a mass limit, and above that limit it fails. Above 1.4 solar masses, the collapse resumes. The question again becomes, what catches it next? The answer is one more rescue, one more piece of physics, one more pause in the staircase, and then, after that, the rescues end. We're going to walk down the next 2 steps quickly, because the rest of the story is where the truly strange physics begins. The next rescue is the neutron star, and the rescue after that, the one that this entire video is named for, is the Planck star itself. Let us go to the neutron star. Let us walk into the regime where an entire mass of a sun is crammed into a sphere 20 kilometers across, and where the rescue is, again, very nearly the answer, and where the limit, again, fails, and where the event horizon, the same horizon Michel wrote down in 1783, finally, after 300 years of being prevented, actually forms. Part 5. The neutron star. When a stellar core exceeds the Chandrasekhar limit, the electrons can no longer hold it open. They are pushed up against the relativistic ceiling of degeneracy pressure, and the ceiling fails, and the collapse resumes. The matter falls, the density rises, and at a certain critical density, about 1,000,000 times higher than the density of a white dwarf, somewhere in the neighbourhood of 10 to the 14 grams per cubic centimetre, the density of an atomic nucleus, something new happens. The electrons, packed into the protons of the falling matter by sheer gravitational pressure, are absorbed by the protons in a process called inverse beta decay. An electron and a proton combine. They produce a neutron and a neutrino. The neutrino flies away, carrying off its small share of the energy, leaving behind a body composed not of atoms anymore, but of pure neutrons, a neutron star. A neutron star is what gets built when the white dwarf rescue fails, and the next rescue miraculously holds. It contains roughly the mass of the Sun, packed into a sphere about 20 kilometers across, the size of a small city. The density is comparable to the density of an atomic nucleus. A single teaspoon of neutron star material weighs about 1 billion tons. The surface gravity is about 100 billion times the surface gravity of the Earth. If you dropped a marshmallow on a neutron star, it would strike the surface with the kinetic energy of an atomic bomb. Even atoms cannot exist on the surface. The gravity is too strong for them. The structure is a sea of neutrons, held up against further collapse by neutron degeneracy pressure. The same Pauli exclusion principle that held the white dwarf together, this time applied to neutrons. For a moment in the late 1930s and the 1940s, the discipline thought this was finally the final rescue. Neutron stars were predicted theoretically by Walter Baade and Fritz Zwicky in 1934, almost immediately after the neutron itself was discovered by James Chadwick in 1932. Zwicky and Baade wrote down, in a brief paper, the suggestion that the energy of supernova explosions might come from the gravitational collapse of a stellar core into a neutron star, with the binding energy of the resulting object released as the supernova event. The paper was speculative. The actual nuclear physics of the proposal would not be worked out until the 1960s. But the idea was there. Above the Chandrasekhar limit, the collapse does not produce a black hole. It produces a neutron star. The rescue holds. The hope continues. Scene moment, immersive, standing on a neutron star at the TOV limit. You're standing on the surface of a neutron star. You're not, of course. Nothing made of molecules can stand here. But imagine for a moment that you could. The crust beneath your feet is a lattice of iron nuclei pressed so tightly together that they are no longer behaving as atoms in any familiar sense. The temperature is something like 1,000,000 kelvins, but you cannot feel it. The heat conducts through the surface so slowly that nothing reaches your skin. The sky above you is doing something strange. The gravity of the body you're standing on is so extreme that the light coming from distant stars is being bent into a halo around your head. Stars that should be behind the neutron star on the opposite side are visible to you above the horizon because their light has curved around the body. The sky is bigger here. The visible cosmos has folded inward, and then, somewhere beneath your feet, somewhere in the core of the neutron star where the density approaches 3 times nuclear density, the rescue you're standing on begins to fail. Not visibly, not with any external sign. The neutron degeneracy pressure that holds the star up has a limit, just as electron degeneracy pressure had a limit, just as material strength had a limit before that. The limit is called the Tolman-Oppenheimer-Volkoff limit, after the 3 physicists, Richard Tolman, Robert Oppenheimer and George Volkoff, who first worked it out in the late 1930s. The exact value is still debated. Current measurements suggest it sits somewhere between 2 and 3 times the mass of the Sun. Above that mass, neutron degeneracy pressure fails. The star cannot hold itself open. It falls. You feel nothing. The collapse from inside happens in milliseconds. The surface you're standing on accelerates downward at significant fractions of the speed of light. The gravitational field at what was the surface increases by orders of magnitude. The escape velocity, which on a neutron star was already about half the speed of light, rises past the speed of light itself. The event horizon forms. From outside somewhere, a distant astronomer sees the surface of the neutron star slow, redden, freeze. From inside, you continue to fall. The horizon is not, for you, a barrier. It is a one-way membrane that you have already crossed before you noticed. End scene moment. This is what happens in physical detail when the neutron degeneracy rescue fails. The collapse resumes. There is no next pause. There is no next rescue available in classical physics. The matter falls inward toward the center, and the equations of general relativity, applied to that fall, point straight at a singularity, a point of infinite density, a region where the equations stop computing. The end of physics, in the classical picture, sitting at the center of an object that, from the outside, has now formed an event horizon. The same horizon Michel wrote down in 1783, the same horizon Schwarzschild derived from general relativity in 1915 and 1916, the same horizon that has been the target of the discipline's 300-year hope to prevent. The horizon, this time, is real. The horizon, this time, actually forms. The rescue has failed. The collapse has continued. The black hole has been built. We know it has been built because we have in our lifetimes observed it. Not directly. You cannot see the interior of a black hole. The horizon is a one-way membrane, but you can see the consequences of one having formed. You can see the gravitational waves rippling out from 2 black holes orbiting and merging. As the LIGO detectors first heard on the 14th of September, 2015, 2 black holes, 136 solar masses, 129 solar masses, colliding 1.3 billion light-years away, sending out a chirp of space-time distortion that arrived at our planet as a tiny but unmistakable signal. You can see the photon ring around the supermassive black hole at the heart of the galaxy M87, imaged for the first time by the Event Horizon Telescope and released to the public on the 10th of April, 2019, a 6.5 billion solar mass body, 55 million light-years away, surrounded by a glowing accretion disk and a dark central shadow. You can see the photon ring around the supermassive black hole at the center of our own galaxy, Sagittarius A star, imaged by the same collaboration and released on the 12th of May, 2022, a 4 million solar mass body, just 26,000 light-years from where you're sitting, with stars orbiting it on Keplerian paths that have been tracked since the 1990s by the teams of Reinhard Genzel and Andrea Ghez, who won the Nobel Prize in 2020 for that very work. You can count, in our galaxy alone, an estimated 40 million stellar mass black holes drifting through the disk, occasionally swallowing a star, occasionally producing a gravitational wave signal that we hear, in our detectors, as a chirp. The horizon is real. The black hole is real. The rescue, in the form of any classical pause, is over. What remains is the question of the interior, the question of what is actually behind the horizon, in the regions general relativity points at but cannot describe. The question Michel could not have asked in 1783, because in his Newtonian framework there was no horizon. There was only a body whose surface was unusually difficult to leave. The question that arrived only when general relativity arrived, and the horizon became a genuine geometric feature of space-time rather than a kinematic accident. The question of what is on the other side. The answer, in classical general relativity, is the singularity, a point of infinite density, a theoretical absurdity. The discipline's 300-year hope to be saved from this answer has, in its original form, failed. The rescue did not come at any of the points the hope expected. The dark star was prevented, but the stars themselves were not. Fusion held the stars open, but only while they had fuel. The white dwarf caught the smaller dying stars, but failed above the Chandrasekhar limit. The neutron star caught the next round of failure, but failed above the Tolman-Oppenheimer-Volkoff limit. The classical rescues are exhausted. The math points at a singularity. The discipline is at the bottom of the classical staircase. But the staircase, it turns out, has more steps. Because in the late 20th century, a new piece of physics arrived. Not from astrophysics, not from general relativity, but from the deep marriage of quantum mechanics and gravity, from the program that is still, in 2026, called quantum gravity. And quantum gravity, in its various forms, has been doing what the discipline did for the previous 300 years. It has been searching for a rescue. It has been searching for a piece of physics that arrives at the very deepest scales, scale 16 orders of magnitude beyond anything the LHC can probe, and that, at those scales, refuses to let the collapse continue. It has been searching, in other words, for a quantum rescue. The rescue, in the loop quantum gravity version of the story, is called a Planck star. It is what we have been walking down the staircase to meet. It is what the next several chapters are about. And it is unlike anything we have met so far, because it is not, in the end, a rescue at all in the sense the discipline has been hoping for. It does not prevent the collapse. It does not prevent the horizon. The horizon has already formed. The collapse is already inside it. What the Planck star does, if it is right, is something stranger. It is a rescue not of the star, but of what is inside the star. It is a preservation. We will return to that word. Let us first walk through the singularity problem in detail. Let us understand exactly what general relativity is predicting at the centre of a black hole, why the discipline cannot accept it, and why the rescue, this time, has to come from somewhere outside the classical theory. Let us go to the singularity. Part 6. The horizon forms. What is an event horizon exactly? We have said it is a one-way membrane. We have said it is a boundary in space-time. We have said that the rescue we have been walking down the staircase to find is, in the end, a rescue not of the star but of what is inside the star, because the horizon, once formed, cannot be undone. But we should be precise about what the horizon is, because the picture in your head is almost certainly wrong, and the picture you need for the next 2 chapters to land is one of the strangest pictures in physics. An event horizon is not a surface. It is not a wall. It is not a layer of any material substance. It is not anything you can touch, or measure locally, or detect as a sudden change in any physical quantity. If you fell through the event horizon around a sufficiently large black hole, where the tidal forces are gentle enough that you would not be torn apart on the way, you would notice nothing in particular at the moment of crossing. There would be no flash. There would be no temperature change. There would be no instrument that would beep. You would look down and see, presumably, your hands. You would look up and see the rest of the universe still visible, still receding above you the way it would in any free fall. The horizon, locally, is not a thing. It is a boundary defined by where light goes, specifically by where the future-directed light rays from any point converge in the geometry of space-time to never escape outward. The horizon is the set of points from which, given the geometry, no future-directed time-like or null path leads to infinity. It is, in the deepest possible sense, a definition rather than a substance. It is a feature of the structure of space-time, not a feature of the matter inside it. What this means for the geometry of the interior is one of the most counterintuitive facts in classical general relativity. Inside an event horizon, the radial coordinate, the coordinate that, outside the horizon, you would describe as distance from the centre, becomes time-like. The time coordinate, the one that outside the horizon you would describe as time, becomes space-like. The roles exchange. What this means, in plainer language, is that for an observer inside the horizon, falling inward is no longer a choice you can decline. Falling inward is the future. The centre of the black hole is not a place. It is a moment. It is something that lies in the future of every observer inside the horizon, in the same way that next Tuesday lies in the future of every observer outside the horizon, and you cannot, by any choice of motion, avoid arriving at it. You can choose to take the long way around. You can choose to fire your rockets. You can choose to do anything you like with your remaining time, but you will, in finite proper time, arrive at the singularity. It will happen to you the way next Tuesday will happen to you. You cannot turn around. There is no space-like direction inside the horizon that leads outward. Outward is no longer a direction in space. It is a direction in time, and that direction is now closed. This is the deepest fact about the interior of a black hole in the classical picture. The interior is not a region. It is a future. The singularity is not a place. It is a moment that every observer inside the horizon is heading toward, and when it arrives, it terminates the observer's world line by terminating space-time itself. This is what general relativity predicts. This is what the singularity theorems of Roger Penrose in 1965 and of Hawking and Penrose together in 1970 established with full mathematical rigour. Under reasonable energy conditions, gravitational collapse must, in classical general relativity, produce a singularity in finite proper time. This is a theorem, not a conjecture, a mathematical consequence of the structure of general relativity applied to a collapsing star. It is the last assumption that is in trouble. The singularity theorems prove that classical general relativity, applied to a collapsing star, predicts its own breakdown. They do not prove that singularities exist in nature. They prove, in fact, the opposite, in a precise sense. They prove that any theory containing them is incomplete. They prove that there must be a more fundamental theory, beneath classical general relativity, that takes over before the singularity actually forms, and that this more fundamental theory must in some way describe what is actually there. The singularity theorems are not a statement about reality. They are a statement about the limits of one of our theories. They are general relativity telling us, in its own language, that it cannot describe its own endpoint. What more fundamental theory? The answer that has been pursued for the longest, with the most resources, and with the most theoretical infrastructure, is some marriage of quantum mechanics and general relativity. Some theory in which the rules of the quantum world apply to space-time itself. This is the program of quantum gravity. It has several major branches. The two most developed are string theory, which arose in the late 1960s as a theory of the strong nuclear force and was repurposed in the 1970s and 80s as a candidate theory of everything, and loop quantum gravity, which arose in the 1980s as a direct attempt to quantize general relativity without reference to any other framework. Both of them claim to describe what spacetime looks like at the Planck scale, the scale at which the smooth geometry of general relativity breaks down, and quantum effects on the geometry itself become unavoidable. Both of them claim, in different ways, that the singularity does not actually form. Both of them have proposed answers for what is actually inside a black hole instead. String theory's answer is the fuzzball, a proposal developed primarily by Samir Mathur of Ohio State starting in the early 2000s. Loop quantum gravity's answer is the Planck star, proposed by Carlo Rovelli and Francesca Vidotto in 2014. This video is about the Planck star, but we should at least note in passing that there is another candidate. The fuzzball says the entire interior of a black hole is filled with a tangled mass of string-theoretic degrees of freedom and that there is, in effect, no singularity and no traditional event horizon. The surface of the body is the fuzz itself. The Planck star says something different. The Planck star says the singularity is averted by a different mechanism, by the discrete grain of space-time itself, and that what sits at the centre of a black hole is a tiny ball of frozen Big Bang density matter, held there by extreme gravitational time dilation. The two pictures are different. They make different predictions, in principle. They both arrive, however, at the same negative answer to the singularity question. Both say no. Callback phrase, first appearance, the rescue that has been hoped for by physicists for 300 years running. The rescue that has been hoped for by physicists for 300 years running, the rescue that prevents the worst object the math can describe, does not arrive at any of the points the discipline expected it to arrive. It does not arrive at the stellar formation stage in the way Michel's dark star was prevented. It does not arrive at the fusion stage, because fusion only holds the star open while it has fuel. It does not arrive at the white dwarf stage, because above the Chandrasekhar limit, electron degeneracy fails. It does not arrive at the neutron star stage, because above the Tolman-Oppenheimer-Volkoff limit, neutron degeneracy fails. It does not arrive at the horizon, because the horizon, once formed, is a one-way membrane, and the rescue, even if it came after the horizon formed, could not save the star itself from the inevitable inward fall. The rescue, in any classical form, did not arrive. The horizon formed. The black hole was built. The 40 million stellar mass black holes drifting through this galaxy are evidence that the rescue, in the form the discipline hoped for, did not come. What did arrive, at the very deepest scales, what the loop quantum gravity program proposes arrives at the Planck density, 16 orders of magnitude beyond anything the LHC can probe, is something else, something stranger than a rescue, something that does not prevent the formation of the black hole, that does not prevent the collapse, that does not prevent the horizon, something that simply, at the very deepest moment of the fall, refuses to allow the singularity to form. The collapse in this picture halts, not at any of the classical pause points, not at any density physics can currently reach in any experiment, but at the Planck density itself, at 10 to the 96th kilograms per cubic meter, the density at which the smooth fabric of space-time, according to loop quantum gravity, gives way to its underlying granular structure. At that density, in this picture, the grain of space-time itself begins to push back. The collapse halts, the matter rebounds, and what emerges, what we now have the rest of this video to describe, is the Planck star. But before we go there, before we walk into the chapter where the rescue, in its new and strange form, finally arrives, we need to do one more thing. We need to walk through the actual deep problem the singularity creates for physics, not just the abstract problem of equations breaking down, but the concrete problem of what happens to all the information that fell into the black hole. We need to walk through the information paradox, because the Planck star, when it arrives, is not just a proposal for what sits at the centre of a black hole. It is a proposal that, if it is correct, resolves one of the deepest open problems in modern physics. And to understand why that matters, we need to understand what the problem is and why it cannot be solved within classical physics, and why a quantum rescue of exactly the kind the Planck star provides may be the only way out. Let us go to the information paradox. Let us go to Hawking. Let us go to the bottom of the staircase. Part 7. The Singularity Problem. In 1974, Stephen Hawking published a paper in Nature titled Black Hole Explosions, with a question mark in his own modest fashion. And in that paper he showed something that has since been considered one of the deepest results in 20th century physics. He showed that black holes are not in fact eternal. He showed that they radiate. The argument was technical. The argument involved quantum field theory and curved space-time, a framework that had been developed in pieces over the previous decade, and that Hawking was, in the early 1970s, the first person to apply seriously to the black hole problem. The essential picture, stripped of its technical detail, was this: even in empty space, even in the vacuum of perfectly empty spacetime, quantum field theory predicts the constant fluctuation of virtual particle pairs. Particle and antiparticle, spontaneously created and almost immediately annihilated in the background of every region of space. Normally these pairs annihilate before they can be observed. They are virtual. They exist only inside the brief window allowed by the uncertainty principle. They do not, in any sustained way, become real. But near the event horizon of a black hole, something strange happens. One member of the pair can fall through the horizon, while the other escapes outward. The escaping particle becomes real. It carries energy away from the black hole. The infalling particle, by the bookkeeping of energy conservation, must have negative energy from the perspective of an outside observer, and so the black hole must have lost a small amount of mass. The black hole is, in this slow, steady way, evaporating. Energy is leaking out. The mass is shrinking, and given enough time, vast amounts of time, 10 to the 67th years for a solar mass black hole, 10 to the 99th years for the supermassive ones, the black hole will eventually evaporate completely. This was a stunning result. For decades after Schwarzschild and through the careful work of Bardeen and Carter and Hawking himself, black holes had been thought of as perfectly black, perfectly stable, perfectly absorbing objects that grew slowly by accumulating matter and that never gave anything back. Hawking's 1974 paper changed that. Black holes were not eternal. Black holes were leaky. Black holes had a temperature, and the temperature was inversely proportional to the mass. Smaller black holes were hotter. Eventually, at the very end of evaporation, a black hole would be so small and so hot that its final moments would be a brief burst of high-energy radiation. The title of Hawking's paper, Black Hole Explosions, was about that final burst. It was suggesting that somewhere in the universe you might be able to detect the explosive death of a small primordial black hole that had been slowly evaporating since the early universe. The detection has not been made in 52 years of looking. The argument, however, is now standard. Hawking radiation is real, in the sense that essentially every physicist accepts it as a feature of the theory, even if it has never been directly observed. Hawking radiation creates the information paradox. When matter falls into a black hole, it carries quantum information, the specific quantum states of all the particles, the specific configuration of all the fields. Quantum mechanics, in one of its deepest principles, says this information cannot be destroyed. The technical name for the principle is unitarity, and it is one of the most rigorously tested features of quantum theory. But Hawking's calculation says the radiation a black hole emits is thermal. It is random. It carries no information about what fell in. It depends only on the mass, charge, and angular momentum of the black hole. When the black hole evaporates fully, all the information about what fell in has apparently vanished. Not just hidden, not just inaccessible, destroyed, violating unitarity. This is the information paradox. This is the deepest open problem in theoretical physics today, by a wide margin. It is the problem that has spawned literally thousands of papers over the past 5 decades. It is the problem that has produced the holographic principle, the AD-CFT correspondence, the firewall paradox, the soft hair proposal, the island formula, the recent page curve calculations of Pennington and Almeri and others. It is the problem that has driven, more than any other, the modern marriage of quantum mechanics and general relativity. And it is the problem that, if the Planck star proposal is right, finds its resolution not in some sophisticated string-theoretic mechanism, not in any deep holographic encoding, but in something very direct. In the fact that the black hole simply does not, in the end, fully evaporate. The information is preserved, in the picture we are walking toward, in the relic that remains. The Planck relic, when we get to it, is the resolution. But we are not there yet. Before we can get to the Planck relic, we need to walk through the actual mechanism by which loop quantum gravity says the singularity is averted. We need to understand what loop quantum gravity is. We need to understand what it says about the structure of spacetime at the Planck scale. And we need to understand how that structure, when applied to the collapsing matter inside a black hole, halts the collapse and produces a Planck star. So here is the situation at the bottom of the classical staircase. The rescue did not arrive at any of the classical pause points. The horizon formed. The collapse continued. General relativity, applied to that collapse, predicts a singularity. The singularity violates physics. Hawking radiation makes the situation worse. Even if the singularity is somehow tolerable, the evaporation of the black hole destroys the information that fell in, which is independently impossible. Both classical general relativity and classical Hawking radiation calculations point at outcomes that quantum mechanics forbids. Something has to give. Either general relativity is wrong about the singularity, or quantum mechanics is wrong about information conservation. Or, and this is the path the discipline has chosen, almost unanimously for the past 50 years, there is a deeper theory beneath both of them, a theory of quantum gravity that resolves the contradiction. The discipline has been searching for that deeper theory for half a century. The two leading candidates, as noted, are string theory and loop quantum gravity. Both have, in their detailed forms, made specific proposals for what happens at the deep interior of a black hole. The string-theoretic proposal, the fuzzball, fills the entire interior with stringy degrees of freedom and replaces the classical horizon with a stringy surface. The loop quantum gravity proposal, the Planck star, leaves the horizon in place, but replaces the singularity with a tiny bounce state of ultra-dense matter held in time dilation. These two pictures are different. They make different predictions in detail, but they share the central feature. Both of them deny the existence of a true classical singularity at the centre of a black hole. Both of them say that whatever is there, it is not infinite density at zero volume. Both of them say that physics continues. Both of them are attempts to be the rescue the classical staircase did not deliver, a rescue not of the star but of physics itself. We are about to walk into the chapter where loop quantum gravity introduces its actual mechanism. We are about to walk into the regime of the Planck length, the Planck density, the Planck time, the deepest scales at which the smooth fabric of spacetime, according to LQG, breaks down into discrete area elements. The numbers we are about to encounter are unfamiliar, and they are difficult to hold in mind because they describe scales that no human experimental apparatus has ever approached. The Planck length is 16 orders of magnitude smaller than the proton. The Planck density is 10 to the 96th kilograms per cubic meter. The Planck time is 10 to the negative 44th of a second. None of these numbers correspond to anything you can hold in your head. They are the floor of physics. They are the layer beneath which the concept of smaller may not make sense, and the concept of faster may not make sense, and the concept of denser may not make sense. Because at those scales, the smooth geometry of spacetime itself, according to LQG, is replaced by a discrete network of quantized area elements that does not have a sensible notion of distance in the way we're used to. This is the regime the Planck star inhabits. This is the regime where the rescue, if it exists, lives. We're about to descend into it. We're about to walk past the floor. We're about to look at what is, by every reasonable measure, the deepest layer of the universe. The Planck length sits at the bottom of every theoretical exploration of quantum gravity. It is, in a sense, the place where physics either ends or transitions into something genuinely new. The Planck star, if it exists, lives exactly there. It is the rescue, finally, if it is right, that the classical staircase did not deliver. It is the answer to the question Michel wrote down in 1783, when he asked what would happen if you made a star whose escape velocity exceeded the speed of light. The answer is, a black hole forms, a horizon develops, the matter falls inward, and at the deepest possible scale, The quantum structure of spacetime itself refuses to allow the collapse to terminate in a singularity. The matter rebounds. A frozen ball of Big Bang density energy is left behind. The rest of the universe lives and dies around it. The fossil persists. But to see that properly, we have to first see the floor. We have to see the Planck scale. Let us walk down there. Let us see the bottom. Part 8. The Planck density. The Planck length is 1.616 times 10 to the negative 35th meters. There is essentially no way to write that number in a form that makes it intelligible. A proton is about 10 to the negative 15th meters across. A femtometer. The Planck length is 20 orders of magnitude smaller than that. Compared to the smallest thing physics has ever directly probed, the resolutions of the Large Hadron Collider, at about 10 to the negative 19th meters, the Planck length is 16 orders of magnitude smaller. For all human purposes, it is indistinguishable from zero. The Planck time is the time it takes light to cross the Planck length. It is 5.39 times 10 to the negative 44th seconds. If a single thought lasts on the order of a tenth of a second, you could string together more than 10 to the 43rd Planck times before that thought completed. There is no experiential vocabulary for this. You simply have to accept the number and continue. The Planck density is 5.155 times 10 to the 96th kilograms per cubic meter. This is the density at which, in loop quantum gravity, the smooth fabric of spacetime breaks down into its underlying granular structure. For comparison, water has a density of 1,000 kilograms per cubic meter. An atomic nucleus has a density of about 10 to the 17th kilograms per cubic meter. A neutron star sits at about that same nuclear density. The Planck density is 79 orders of magnitude beyond that. It is the density you would get if you compress the entire visible universe, every star, every galaxy, into a region about the size of a marble, and then squeeze that marble by another 79 orders of magnitude. This is the regime in which, according to the loop quantum gravity proposal of Rovelli and Vidotto, something new happens. At this density, the smooth equations of general relativity, which have been telling us throughout the previous chapters that the collapse must continue toward a singularity, are no longer the right equations. The right equations at this density are the equations of loop quantum cosmology, the cosmological version of loop quantum gravity, originally developed in the early 2000s by Abhay Ashtekar and others as a quantum description of the Big Bang. And in those equations, at this density, an entirely new term appears, a term that does not exist in classical general relativity, a term that arises from the discrete granular structure of space-time itself, a term that acts, in the equations, like a pressure pushing outward, a term that, at the Planck density, becomes large enough to halt and reverse the collapse. Ambient zone. Slow visual descent to the Planck scale. Imagine, if you can, what it would be like to descend toward the Planck scale. Imagine starting at your own body, the height of a human being, about 1.5 meters. Imagine zooming in. The skin of your hand becomes visible as a complex landscape, ridges and valleys, follicles and cells. Imagine zooming in further. The cells become visible. Bags of fluid, intricate machinery, ribosomes building proteins, mitochondria producing energy. Imagine zooming in further. The molecules become visible. Long chains of carbon and hydrogen, folded into shapes that determine their function. Imagine zooming in further. The atoms become visible. Clouds of probability, electrons in their orbitals, a small dense nucleus at the center. Imagine zooming in further. The nucleus resolves into protons and neutrons. Imagine zooming in further. The protons and neutrons resolve into quarks, bound by gluons. Imagine zooming in further. You have now arrived at the resolution of the Large Hadron Collider. You have descended through 21 orders of magnitude. Almost everything that matters in chemistry and biology and medicine and engineering is somewhere in the levels you have already passed. But you have not yet reached the Planck scale. You're still 16 orders of magnitude away. If the descent so far has felt long, you're about to do it again 4 more times. Each time, you will be diving into a regime smaller than any physics experiment has ever probed. Each time, you will be passing through layers of physics that, as far as we know, may not have any substance. We have never measured them. We have never seen them. We have never had any direct evidence that they exist. We are descending now into theoretical territory. The numbers continue to count down. The exponents grow more negative. The scale shrinks. And finally, at 10 to the negative 35th meters, the descent stops. You have arrived. You're at the floor of physics. What is here? According to loop quantum gravity, what is here is not nothing. What is here is not smooth, empty space. What is here is a network of discrete area elements, each one quantized, each one with a definite size determined by the fundamental constants of nature. The network is what space, on small enough scales, actually is. The smooth geometry of general relativity, the smooth metric tensor that describes space-time in textbooks and in equations and in classical calculations, is, in this picture, an emergent feature of the network on large scales. The way the fluid flow of a river is an emergent feature of the discrete molecular motion of water molecules. The way the smooth wave on a beach is an emergent feature of countless discrete water molecules pushing on each other. The way the smooth temperature of a gas in a room is an emergent feature of countless discrete molecular collisions. Space, at the Planck scale, is the same kind of phenomenon. The smoothness is the illusion. The grain is the substance. This is the central claim of loop quantum gravity, and it is the claim from which the Planck star rescue derives. Because if space at the Planck scale is granular, then density itself has an upper limit. You cannot pack matter more tightly than the space-time grains will allow. The granularity itself pushes back. It pushes back the way the discrete molecular structure of water pushes back when you try to compress water by some absurd ratio. The water becomes incompressible at some density set by the molecular structure. Space-time in this picture is the same. At the Planck density, the granular structure pushes back. The collapse cannot continue. The matter falling inward in a black hole encounters, at this density, an effective anti-gravitational pressure arising from the discreteness of space-time itself. The pressure is enormous. The pressure is enough to halt the collapse. The pressure is enough to reverse it. End ambient zone. This is what Rovelli and Vidotto worked out in their 2014 paper in the International Journal of Modern Physics D, titled simply Planck Stars. They took the cosmological bounce equation that had been derived by Ashtekar and others, the equation that, applied to the early universe, replaces the Big Bang singularity with a bounce from a previous contracting phase, and they applied it locally to the collapsing matter inside a black hole. The argument was a semi-classical one. They were treating the matter as smooth and continuous, and they were treating the loop quantum gravity correction as a modification to the standard general relativity equations. This is an approximation. They acknowledged that it was an approximation. The fully quantum picture of a collapsing black hole is something nobody has, including them. But within the approximation, the answer was clean. The collapse halted at the Planck density. The matter bounced. What emerged was an object, a tiny, dense, fossilized object, that they named a Planck star. The size of the object depends on the mass of the original collapsed star. For a stellar mass black hole, a few solar masses, the Planck star is about 10 to the negative 12th meters across, 1 trillionth of a meter, about 1/10,000th of the diameter of a hydrogen atom, small, but, and this is the key fact, much larger than the Planck length itself, 23 orders of magnitude larger. The Planck star is not at the floor of physics. It is well above the floor. It is enormously above the floor, relatively speaking. It is not a singularity, not a Planck-scale object, not anything that pushes against the boundaries of our theoretical descriptions. It is a comfortable, self-contained, semi-classical object that, by ordinary standards of quantum gravity, is entirely tractable. It is just very, very small. And inside this very small object, inside this trillionth of a meter, sits the entire mass of the original collapsed star. Several suns' worth of matter compressed into 1/10,000th of a hydrogen atom, at a density of 10 to the 96th kilograms per cubic meter. The Planck density. The density of the very early universe. The density of the first 10 to the negative 44th seconds after the Big Bang. The Planck star, in this sense, is a fossil. It is a fossil of the conditions that existed in the universe during the first instant after the Big Bang. It is a fragment of the beginning, preserved at the heart of every black hole that has ever formed, held there by a piece of physics that is older than every word in human language. The grain of space-time itself, refusing to let the collapse continue, refusing to let the conditions of the first instant be diluted, holding them in place forever. We have, in this part, set up the deep mechanism. The next part is where it actually happens. The next part is where we fall through the horizon of a stellar mass black hole, descend toward the centre, and watch, in the deepest seen moment of the video, the bounce occur, in the rest frame of the collapsing matter, in the time it takes light to cross a single Planck length. We're about to witness, in the proper frame, what is in fact the central event of this entire night. We're about to see the rescue. We're about to see the Planck star form. Let us go inside. Part 9. The Bounce. Let us go inside. Let us fall. Scene moment. Immersive. Falling past the event horizon. You're falling past the event horizon of a stellar mass black hole. 20 solar masses. The horizon, for an object of that mass, is 60 kilometers across. The radius is about 30 kilometers, comparable to the size of a small neutron star, comparable to the size of a small city on Earth. You're falling toward it from a comfortable distance, having been chosen, for the purposes of this scene, as the observer who gets to make the descent that no observer has ever actually made, and could ever, in principle, report back from. You are falling freely. There is no acceleration you can feel in your own frame, because in free fall the only acceleration is gravity, and you and your reference frame are accelerating together. Locally, in the language of general relativity, you are weightless. You're an inertial observer. Your clock ticks at its normal rate. Your hands look like your hands. The cabin around you, if you're in a cabin, if there's anything around you, feels stable and still. The view, however, is not normal. The view, as you approach the horizon, becomes increasingly distorted. The light from the rest of the universe, as the gravitational lensing intensifies, is being bent into a smaller and smaller cone above your head. The stars and galaxies and cosmic microwave background, the entire visible cosmos, are being compressed into a shrinking circle in the direction you came from. Below you, in the direction of the black hole, is darkness. Not the darkness of absence of light, but the darkness of geometry. No light can reach you from inside the horizon, because there is nothing inside the horizon to emit light back outward. The geometry itself routes all light inward. You see increasingly only the universe behind you. You see increasingly less of it. The cone shrinks. The visible cosmos compresses to a point. The point intensifies. Blue shifts as the entire incoming light cone of your past arrives at your present moment, becomes a brilliant pinprick of compressed cosmic light at the top of your vision. You cross the horizon. You feel nothing. There is no event in your local frame. The pinprick of compressed cosmic light continues to recede above you. You continue inward. Outside somewhere, but the word outside no longer means quite what it used to. Somewhere, a distant astronomer watching the surface of the black hole sees your image redshift, slow, freeze. From their perspective, you never quite reach the horizon. Your image is plastered, frozen, on the surface of the black hole, redshifting toward zero frequency over the entire remaining lifetime of the universe. From your perspective, you have already crossed. The horizon, locally, was nothing. You continue inward. You begin to feel the tidal forces. Tidal forces are the differential gravity between your head and your feet, or between your left side and your right side. For a stellar mass black hole, the tidal forces at the horizon are already extreme. You would be spaghettified, stretched into a long thin line before reaching the horizon. We're ignoring this for the purposes of the scene. We're imagining that you are infinitesimal, a single particle, immune to differential stretching. We're imagining that you continue, intact, toward the center. Your clock continues to tick at its normal rate locally. The geometry continues to route all your future paths inward. The center is in your future. You cannot turn around. You're heading toward it the way you head toward next Tuesday. The density of matter around you rises. You're now in the region of the original collapsed star, the part that, when the horizon formed, was still falling. The matter around you is falling with you, on parallel trajectories, all of you heading toward the center together. The density rises. From the density of a neutron star to 1,000 times nuclear density to 1,000,000 times to 10 to the 25th times nuclear density to 10 to the 50th times. Each rise compresses the matter further. Each rise pushes you closer to the regime where, according to loop quantum gravity, the granular structure of spacetime becomes important. You continue to feel nothing. You're still in your local inertial frame. Locally, in your own clock, the descent has taken, let us say, a millisecond, maybe 2, maybe 10. Time, locally, has barely moved. You arrive at the Planck density. The density around you is now 10 to the 96th kilograms per cubic meter. Everything that was in the original collapsed star is now packed into a region about 1/trillionth of a meter across. You're in the middle of it. The trillionth of a meter is, by every classical measure, vanishingly small. But it is at the local scale you're now experiencing comfortable, mostly empty, mostly far from any boundary. You're inside the Planck star. And then, in the time it takes light to cross your own location, about 10 to the negative 20th seconds, the rescue arrives. The granular structure of spacetime at the Planck density refuses to let the collapse continue. The discrete area elements push back. An effective anti-gravitational pressure appears, sourced not from any matter field, not from any classical force, but from the discreteness of spacetime itself. The pressure is enormous. The pressure is greater than the gravitational crush. The collapse halts. The matter, instantaneously in your frame, reverses direction. What was falling inward is now moving outward. The compressed Planck density matter is expanding. The trillionth of a meter is, locally in your frame, starting to grow. This is the bounce, the moment, in the proper frame of the collapsing matter, when the rescue finally arrives. This is what Rovelli and Vidotto worked out in their 2014 paper. The collapse halts at the Planck density. The matter rebounds. What emerges is a white hole, the time reverse of the black hole that formed it. The horizon reverses direction. The matter expands outward, carrying its information with it. In your frame, this entire bounce, the moment of arrival, the moment of pressure, the moment of reversal, the moment of expansion, takes about 10 to the negative 20th seconds, a tiny fraction of a second, faster than any chemical reaction, faster than any neural process, faster than any thought. The bounce is, locally, instantaneous. You barely notice it. You go from falling to rising, and then, in another local fraction of a second, you're heading outward, the expanding white hole carrying you and the rest of the original star's matter outward at near light speed. The geometry having reversed its orientation, the inward trajectories now becoming outward trajectories, the future now being escape rather than fall. End scene moment. In your frame, then, the entire history of the black hole, from the formation of the horizon, to the descent, to the Planck density bounce, to the white hole emergence, takes about a millisecond, maybe 10, maybe 100, some small fraction of a second in the proper time of the collapsing matter from horizon to horizon in your frame. But in the frame of an outside observer, watching from a comfortable distance, none of this happens. None of this is visible. None of this, in the outside frame, takes a millisecond. None of it takes a second. None of it takes a year. None of it takes 1 billion years. In the outside frame, the entire bounce, is stretched by gravitational time dilation into something that is, by every reasonable estimate, longer than the current age of the universe by tens of orders of magnitude. The bounce from the outside takes on the order of 10 to the 64th years. The bounce from the outside is frozen. This is the key fact. This is the strange and beautiful and difficult fact that makes the Planck star such a peculiar object from the outside. Inside the horizon, in the proper frame of the matter, the bounce happens fast and total. Outside the horizon, in the frame of a distant observer, the bounce is, for all practical purposes, eternally suspended. The Planck star from the outside is not a transient object. It is a fossil. It is a frozen fragment of the conditions of the very early universe, held in place by the most extreme gravitational time dilation in the known cosmos. It is preserved. And here is the consequence. Every black hole in the visible universe, every one of the 40 million stellar mass black holes in this galaxy, every one of the supermassive black holes at the centre of every other galaxy we have ever observed, every one of the primordial black holes that may or may not have formed in the early universe, every single one of them contains, at its centre, on this picture, a Planck star. A trillionth of a metre-wide pocket of Planck density matter, a frozen fragment of the universe's first instant, preserved, motionless, for 10 to the 64th years, by gravity so extreme that the rest of the cosmos will live and die before that fragment has finished its rebound. The night sky, if loop quantum gravity is right, is full of these. The night sky is studded with fossilized fragments of the Big Bang. Every black hole is a sealed time capsule from the moment the universe began. The horizons surrounding them are the seals. The time dilation is the preservation mechanism. The granular structure of spacetime is the chemistry. And the result, if you could somehow see it from the outside on a long enough time scale, is a universe in which the bounce flashes, the white hole emergences, the moments when the Planck star finishes its rebound and breaks out. Those moments are still happening, all around us, all the time, somewhere. They're simply too dilated to see in our own observational window. The bounce, from our perspective, is forever about to happen, and never quite happens. The fossil persists. We will, in the next chapter, sit with this fact. We will sit with the fact that every black hole is a time capsule. We will sit with the fact that there are 40 million of them in this galaxy alone. We will look up at the night sky, at the broad band of the Milky Way, and we will understand on the picture we are constructing tonight that the band of the Milky Way is, secretly, a graveyard of beginnings. Each black hole is a fossil. Each black hole is a sealed pocket of the first instant. The cosmos, on this view, is not running down toward heat death. The cosmos, on this view, is filling slowly with preserved fragments of its own beginning. There is something almost dignified about this. There is something almost tender about it. The universe is not, on this view, throwing things away. The universe is, in its slow, patient way, storing them. Let us go to the second emotional anchor. Let us sit with the 40 million. Part 10. The Frozen Star. There are, according to the most recent statistical estimates, somewhere on the order of 40 million stellar mass black holes in our galaxy alone. The number comes from population synthesis models of stellar evolution, applied to the Milky Way's known stellar populations. The Olejak, Belczynski and Holtz 2020 paper in Astronomy and Astrophysics is one of the standard references. The number is uncertain at the factor of 2 level. It could be 20 million, it could be 100 million. It is, for our purposes, of order 10 to the 7th. tens of millions, in this one galaxy. Drifting through the disk, scattered through the halo, lurking near the galactic centre where Sagittarius A star, the 4 million solar mass supermassive one, anchors the whole rotation. Emotional anchor, existential, the 40 million. The night sky you see, if you stand outside on a dark night somewhere far from city lights, looks like a scatter of points. The brightest of those points are stars, mostly nearby ones, mostly within a few hundred light years. The dimmest of them, in the band-like streak we call the Milky Way, are stars further away, often many thousands of light years, often part of structures we cannot resolve individually. The band-like streak itself is the plane of our galaxy, seen edge on, the disk of stars and dust and gas in which our solar system sits. It is full. It is dense with light. There are, by the best counts, somewhere between 100 and 400 billion stars in the Milky Way. What you cannot see, in that sky, is the 40 million black holes that share the disk with those stars. They do not emit light. They cannot be seen directly. They drift through the same regions as the stars, formed from the same material, travelling on similar orbits, occasionally passing close to other stars, but more often spending eons in the relative emptiness between systems. If you could somehow see them, if there were a way to render every black hole as a luminous point on the same sky you're looking at, the night sky would suddenly be denser. Every 40,000 stars or so would have somewhere in its vicinity a black hole companion you could not previously see. The Milky Way would look more crowded than you knew, and every one of those black holes, if loop quantum gravity is right, contains at its centre a sealed fossil of the universe's first instant. Everyone. All 40 million. This is the existential weight of the Planck star proposal. The proposal does not say there is one. It does not say there are a few. It says there is one inside every black hole in the visible universe. 40 million in this galaxy. Tens of trillions, on a rough estimate, across the entire observable universe. Every galaxy contains its own population. Every supermassive black hole at every galactic centre contains one of its own. Every primordial black hole that may have formed in the early universe contains one. Every one of them a sealed pocket of conditions that have not existed anywhere in the cosmos since the first 10 to the negative 44th seconds. The night sky is, on this view, full of fossils. The night sky is a graveyard, but it is a graveyard in the most generative sense of the word. Not a place where things are merely ended, but a place where the first conditions of the universe have been preserved against all odds by the very physics that destroyed everything else around them. There is, in this picture, an almost geological quality to the cosmos. The same way the rocks of the Earth contain fossils of the life forms that lived before us, the cosmos contains, in its black holes, fossils of its earliest conditions. The Earth's geological fossils are preserved by chance and chemistry. The cosmos's Planck star fossils are preserved by something far more reliable, by gravity itself, with absolute fidelity, for 10 to the 64th years per object. The Earth's fossils degrade eventually. The Planck star fossils do not degrade. They simply sit, frozen, while the universe ages around them. The stars they were once part of are long gone. The galaxies those stars lived in will, in the deep future, disperse. The cosmic microwave background will redshift into nothing, but the Planck stars persist. Those are still there. Enad emotional anchor. Callback phrase, return. The rescue that has been hoped for by physicists for 300 years running. The rescue that has been hoped for by physicists for 300 years running, the rescue that prevents the worst object the math can describe, turns out, in this picture, not to be a rescue of the star. The star is lost. The horizon forms. The matter falls. The collapse continues all the way to the Planck density. The rescue, in this picture, arrives only at the very last possible moment, only at the very last possible scale, only when the matter has already passed every classical safeguard and entered the regime where no theory but quantum gravity itself can describe it. And the rescue, when it arrives there, is not a rescue of the star. It is a rescue of what is inside the star. It is a preservation. This is the shifted meaning of the callback. We have been calling it a rescue all along, but the right word, the deeper word, the word the journey has been pointing at the whole time, is not rescue. It is preservation. The Planck star does not save the star from collapse. The star has already collapsed. The Planck star saves what is inside the matter, the information, the fundamental conditions, the very atomic structure of the first instant, from being destroyed by the singularity. The Planck star is the universe's quiet refusal to let the first instant be erased. The Planck star is the place where the conditions of the Big Bang are still happening, are still going on, are still being maintained in tiny preserved pockets inside the heart of every black hole. This is, in a sense, the most consequential reframing of 300 years of hope. The hope was that nature would prevent gravitational collapse. Nature did not prevent it. The horizons exist. The black holes exist. The collapse went all the way down. But at the bottom of the collapse, at the very deepest scale, what the discipline now believes, if loop quantum gravity is right, is that the universe refused to throw the information away. The universe held on to it. The universe wrapped it in time dilation and stored it. The Planck star is the storage. The black hole is the safe. The horizon is the door. And every time a star dies and forms a black hole, the universe is, on this view, doing something quietly, structurally generous. It is preserving the conditions that made the universe possible in the first place, and storing them where they will not be touched, for longer than the rest of the cosmos will exist. This is what makes the loop quantum gravity picture, for many of the physicists who work on it, so attractive. It is not just that the picture solves the singularity problem. It is not just that it resolves the information paradox. It is that the picture, in its deepest implications, suggests that the universe is structured to preserve its own beginning. That every black hole is a kind of monument, a kind of vessel, a kind of long-term archive of the conditions from which everything else emerged. That the fossils are not accidents. That the fossils are in some sense what the universe is for. We should not get too poetic about this. The mathematics is the mathematics. The proposal is a proposal. It may be wrong. It may turn out in 20 years or in 200 that loop quantum gravity is not the correct quantum theory of gravity, that the Planck star is a beautiful intuition that does not survive the deeper theory, that something quite different is happening at the centre of a black hole. The skeptical interpretation is real, and we will come back to it before the end of the night, but for now, sit with the picture. Sit with the night sky, full of preserved beginnings. Sit with the 40 million in this galaxy alone. Sit with the rescue that turned out in the end to be a preservation. Sit with the rebranding of 3 centuries of hope. The hope was that the universe would refuse to build the worst object. The reality, on this picture, is that the universe built the object, but built it as a vessel, as a vault, as a storage device for the conditions of its own beginning. The black hole is not the end of physics. The black hole is the place where the beginning is hidden. We will, in the next chapter, look at what happens to the Planck star over even longer timescales. We will look at what happens when the surrounding horizon evaporates. We will look at the 2024 update to the picture, in which the Planck star itself is shown to persist long past the Hawking evaporation lifetime of the black hole that contains it, in the form of a Planck relic. A Planck-length shell holding a 1 trillion times larger interior, locked in a quantum superposition of black hole and white hole, possibly accounting for some fraction of dark matter, possibly resolving the information paradox in its sharpest form, possibly representing the actual long-term inheritance of the visible universe in the deep future. The picture, in the 2024 update, becomes even stranger than what we have just walked through. The fossils, it turns out, do not even need their original horizons to survive. They can survive the horizons themselves. Let us go to the relic. Let us go to the long-term fate of the Planck star. In a universe 10 to the 90th years old, when every other structure has come undone. Part 11. The Planck Relic. In 2014, when Rovelli and Vidotto first published the Planck star proposal, the picture they had was a kind of frozen midway point. The Planck star, in their original framing, was the bounce caught in the middle of its rebound, the moment of collapse reversed to expansion, held in extreme time dilation, eternally about to break out. The original paper did not, in detail, address the question of what happens at the very end of the host black hole's lifetime, when the surrounding horizon has finally evaporated all the way down via Hawking radiation. The original paper left that for later work. Over the following decade, that work was done. The picture was refined. A more complete version emerged, and in 2024, Rovelli and Vidotto published an update, building on their 2018 paper on small black and white hole stability, which had introduced the idea of the Planck relic, that gave a sharper version of the long-term fate of the Planck star. The picture is this. The surrounding horizon of a Planck star-bearing black hole shrinks over time via Hawking radiation. The shrinking is extremely slow for stellar mass black holes, where the lifetime is on the order of 10 to the 67th years, and even slower for supermassive black holes, where the lifetime can be 10 to the 99th years or longer. But over those vast timescales, the horizon does shrink. Mass is gradually carried away by the thermal radiation. The black hole loses mass slowly at first, then faster as it gets smaller and hotter. The shrinking accelerates. Eventually the horizon approaches the Planck scale itself, the scale where loop quantum gravity's discrete structure becomes important. And here, in the loop quantum gravity picture, something new happens. The horizon, in this picture, has its area quantized in units of approximately the Planck area, 10 to the negative 70th square meters. The area cannot, in the discrete picture, shrink continuously. It can only step down in discrete amounts, and below a certain threshold, near one Planck area, it cannot step down further. The Hawking evaporation, which would in the classical picture continue all the way to zero, stops. The black hole does not evaporate completely. What is left behind is a Planck scale residue, a horizon roughly 1 Planck length across containing the inner Planck star. This residue is called a Planck relic, and it has a property that is, even by the standards of the rest of this video, deeply strange. The horizon of the relic is 1 Planck length across, 10 to the negative 35th meters, the smallest possible scale in physics. But the interior Planck star is, as we established back in Part 8, about 10 to the negative 12th meters across. The interior is 23 orders of magnitude larger than the shell. The interior is 100 billion trillion times bigger than the supposed container. How is this possible? The answer is the same property we encountered when we first walked through the interior of a black hole. Inside the horizon, the radial coordinate is time-like. Distance, in the spatial sense, no longer applies in the way we're used to. The interior is not, properly speaking, a region of space. It is a region of time, a future-pointing region into which all paths inside the horizon converge. There is no contradiction in a future being arbitrarily larger than the present that opens onto it. In the same way, there is no contradiction in your own remaining life, measured in years, being far larger than the duration of any single moment you are currently living through. The Planck relic's interior is a future. The future is large. The opening, the horizon, is small. That is the geometry of black holes. That is what general relativity, and now loop quantum gravity, says is going on. The relic, then, is a Planck-scale shell holding a trillion times larger pocket of Planck density frozen matter. It is by far the strangest object in the proposal. It is smaller than any structure physics has any reason to believe in, on its outside. It is comparatively gigantic on its inside. It contains, locked away, the entire information content of every particle that fell into the original black hole, preserved in the interior pocket, unable to leak out across the Planck-scale horizon, immortal on the time scale of the rest of the cosmos. And then there is the further strangeness. As the shrinking horizon approaches the Planck scale, quantum effects begin to dominate. Among those quantum effects is the possibility of tunneling between different geometric configurations. A Planck scale black hole state and a Planck scale white hole state are, in the loop quantum gravity description, separated by a finite action barrier, and a finite action barrier, in quantum mechanics, can be tunneled through. The relic can quantum tunnel from a black hole configuration to a white hole configuration, and then back, and then forward again, indefinitely. The relic, in the cleanest version of the 2024 picture, exists in a quantum superposition of black hole and white hole. It is not classically one or the other. It is both, simultaneously flickering between them on Planck timescales, frozen in a state that is, in human language, simultaneously about to swallow and about to explode. This is what is left, at the end of the black hole's life, not nothing. Not a final flash of Hawking radiation followed by emptiness, not a violation of unitarity, not the destruction of information, not any of the bad outcomes that the standard Hawking evaporation picture seems to lead to. What is left is a Planck-scale knot of space-time, holding a relatively enormous pocket of preserved Big Bang density matter, locked in a quantum superposition of two opposite gravitational futures, completely inert by ordinary standards but absolutely full of information. And these things, in the loop quantum gravity picture, are stable. They do not evaporate further, they do not decay, they simply sit. They sit through the deep future of the universe, through the eventual evaporation of every other black hole, through the dispersal of every galaxy under the accelerating expansion, through the red-shifting of the cosmic microwave background into thermal silence, through the slow extinction of every star and the eventual proton decay, if proton decay happens, of every nucleon left in the cosmos. The relics persist past all of that. They are the longest-lived objects the universe is capable of producing. They are the inheritance of the visible universe. Scene moment, immersive, 10 to the 90th year universe. Try to imagine what the universe looks like in 10 to the 90th years. The current age of the universe is 1.4 times 10 to the 10th years. We are asking you to imagine a time 80 orders of magnitude further in the future. Every star has burned out. Every white dwarf has cooled to ambient temperature. Every solar mass black hole has finished its Hawking evaporation, leaving behind its Planck relic. The supermassive black holes are still finishing. The galaxies have long since dispersed. What used to be the Milky Way is a sparse fog of evaporating compact remnants drifting through an exponentially expanding cosmos. You're floating somewhere in what was once a galaxy. There is no light. The cosmic microwave background has redshifted to wavelengths so long it is no longer detectable. The universe is, by every ordinary measure, dead, but suspended in this dark vacuum, in numbers you cannot count, are the relics. They are too small to see individually. Planck-scale objects, 10 to the negative 35th meters across, with no electromagnetic interaction. They would be invisible to any instrument, but they are there. Every former black hole has left one behind. They drift slowly relative to one another, occasionally tunneling between black hole and white hole configurations, occasionally, in the strongest versions of the picture, performing the bounce flash that is, perhaps, what fast radio bursts are. They are the last things. They are the universe's persistent inventory, and inside each one is a fossil, a pocket of Planck density matter, a frozen fragment of the universe's first instant. The relics are, in the end, what the universe held on to when it had to let everything else go. End scene moment. Now think about the implication for the present. We are not in 10 to the 90th year universe. We are in 14 billion year universe. We are in the early universe by the standards of these relics. The relics, if they exist, are still mostly in their black hole phase. The original stellar and supermassive black holes are still around. The horizons are still surrounding them. But primordial black holes, the small black holes that may have formed in the very early universe, from density fluctuations during inflation before the first stars existed, those, if they had small enough initial masses, have already finished their evaporation. They have already become relics. They are out there, in our universe, today, in numbers we cannot directly determine, distributed through galactic halos and intergalactic space. And here is the speculative consequence. If primordial black holes formed in sufficient numbers, and if a substantial fraction of them have already converted to Planck relics, then those relics might collectively constitute some fraction of the dark matter we have been measuring for decades. The rotation curves of galaxies, the gravitational lensing of galaxy clusters, the structure of the cosmic microwave background, all of these have been telling us for 50 years that there is more matter in the universe than the luminous matter we can see. 5 times more, roughly. What is it? Various candidates have been proposed. Weakly interacting massive particles, axions, sterile neutrinos, primordial black holes themselves. The Planck relic as dark matter proposal is a variation on the primordial black hole hypothesis, with the twist that the dark matter consists not of intact primordial black holes, but of their evaporation residues, the relics. The mass is in the relics, the lensing is in the relics. The galactic rotation is, on this picture, anchored by relics. The numbers are uncomfortable. To explain dark matter this way, you need on the order of 10 to the 50th to 10 to the 55th relics in our galactic halo. The primordial black hole population would have had to be vast and tilted towards small masses. Current constraints from microlensing, cosmic microwave background distortion, and gravitational wave searches rule out parts of that parameter space, and the Planck relic dark matter window is therefore narrow. The proposal is not ruled out. It is also not strongly favoured. It sits as one of several plausible exotic candidates. But it has a quality the others do not. Axions, sterile neutrinos, weakly interacting massive particles. These all require new fundamental matter beyond the standard model. The Planck relic proposal requires only the standard model plus quantum gravity, both of which are independently motivated. It does not invent new stuff. It works with what is already there. This is one of the reasons the Rovelli-Vidotto program has attracted serious attention. It is unusually economical. It takes the smallest possible set of assumptions and gets out of them the resolution of the singularity, the resolution of the information paradox, a candidate for dark matter, a possible source for fast radio bursts, and a picture of the deep future populated by these strange preserving relics. It may be right, it may be wrong. There is no current way to directly check, but it has, woven into its mathematics, the quiet idea that the universe is the kind of cosmos that, when it builds an object as destructive as a black hole, also builds a fossilizing chamber that preserves the conditions of its own beginning forever. The universe is not, on this picture, hostile. The universe is, in its weirdest and deepest layers, a place that holds on to things. We have walked, in 11 parts, from John Michel's dark stars in 1783 to the Planck relic in the deep future. We have walked down the staircase of failed classical rescues, through the formation of the event horizon, past the singularity problem and the information paradox, and into the proposal that may, finally, be the rescue the discipline has been waiting for. Not a rescue of the star, but a rescue of what was inside it. The fossils, the frozen first instants, the relics. What remains is the question of whether any of this is true. What remains is the question of whether the loop quantum gravity picture is the correct picture of nature, or whether it is one of several beautiful proposals that will eventually be replaced by a deeper, or simply different theory. What remains is the question of whether we will ever be able to check. The Planck scale is 16 orders of magnitude beyond anything the LHC can probe. The interior of a black hole is, by construction, beyond observational reach. The proposed observational signature, fast radio bursts as bounce flashes, is contested. The proposed cosmological signature, Planck relics as dark matter, is statistical at best. The honest answer to the question we started with 300 years ago in a country parsonage in Yorkshire is that we have a beautiful theoretical picture, and we do not yet have any reliable way to find out whether it is true. That is the mystery that remains. That is the place we arrive at the end of 3 centuries of asking and being wrong. We have possibly the answer. We do not yet have any reliable way to know whether we have the answer. The question of what is inside a black hole turns, in its deepest form, into a question about what we are allowed to know about the universe we live in. Let us go to the last chapter. Part 12. The mystery that remains. What is at the centre of a black hole? The honest answer, the one any responsible physicist will give you if you ask them at a conference at the end of a long day, with a glass of wine in their hand, is that we do not know. We do not know what is at the centre of a black hole. We have never been able to look. We will never be able to look in any direct sense, because the geometry of black holes is constructed so that information cannot return outward across the horizon. The question is, in the strictest possible sense, observationally inaccessible. It is one of the only questions in physics that is structurally beyond our reach. We can ask it. We cannot, in any direct way, answer it. What we can do, and what the discipline has been doing for half a century, is develop theoretical pictures of what is consistent with the laws of physics we already know. We can ask, what proposals are consistent with everything we know, with general relativity in the appropriate limit, with quantum mechanics, with information conservation, with the gravitational wave ring-down signatures we have detected, with the photon ring images the Event Horizon Telescope has captured, and we can ask, which of those proposals is independently motivated by progress in quantum gravity? The Planck star as a proposal comes out of this kind of asking. It is one of several proposals that, by the standards of consistency with what we know, are admissible. It has several attractive features. It is parsimonious. It requires only loop quantum gravity, which is independently motivated, and primordial black holes, which are independently motivated. It resolves the singularity problem in a clean way. The granular structure of spacetime halts the collapse. It resolves the information paradox in a clean way. The Planck relic preserves the information indefinitely. It offers a candidate for dark matter that does not require any new particle physics. It offers a candidate source for at least some fast radio bursts. It produces a picture of the deep future that is, in its own way, dignified. The cosmos persists in the form of these preserved relics after every other structure has come undone. But the picture is not at present verifiable. The Planck scale is 16 orders of magnitude beyond the resolution of the Large Hadron Collider. There is no foreseeable experimental probe that will reach it. The Planck relic as dark matter proposal sits in a narrow window of parameter space that current observations cannot decisively confirm or rule out. The fast radio burst connection is contested. The magneto model has been ascendant since the SGR 1935+2. Num-phosphor detection in April 2020, and while the Planck star bounce model is not ruled out for the subpopulation of one-off bursts, it is not the leading explanation. The skeptical reading of the entire picture, that it is a beautiful mathematical extrapolation into a regime where physics has never been tested, and that we have no business taking it as the answer, is, by ordinary scientific standards, the safest position. This is the place we arrive at the end of 300 years of asking. We have, in the loop quantum gravity picture, possibly the answer. We do not have, and may never have, a way to know. There is something humbling about this. Every generation of physicists has hoped for a rescue, and every generation has watched the math force them past their hope into territory they did not want to enter. Michel hoped giant dark stars would not exist. Fowler hoped the white dwarf would catch the dying stars. Eddington hoped the white dwarf would catch all of them. He was wrong, publicly and badly wrong, and he hurt a brilliant younger physicist in the process. The discipline kept hoping anyway. The neutron star was the next hope. It also failed. What the discipline did not anticipate, perhaps could not anticipate, is that the rescue, in the form it finally arrives in, if it arrives at all, if the loop quantum gravity picture is right, is not a rescue of the star, but a rescue of what is inside the star. The star is lost. The horizon forms. The collapse continues to the Planck density. The matter rebounds, but only in a frame so deeply time-dilated that the rebound, from the outside, is essentially eternal. What is preserved is not the star. What is preserved is the information the star carried with it through the horizon, and beneath the information, at the very deepest level, is a fossilized fragment of the universe's first instant. The conditions of the Big Bang itself, held, frozen, by gravity so extreme that the rest of the cosmos will live and die before the bounce is completed. Held and held and held. This is the shifted form of the rescue. The hope, 3 centuries old, was for a piece of physics that would prevent the worst object the math can describe from existing. The reality, on this picture, is that the worst object exists in numbers, exists in tens of millions in this galaxy alone. But that the universe, having allowed it to exist, also built into it a mechanism for preserving the conditions from which the universe itself emerged. The black hole is not the end of physics. The black hole is the place where the beginning is hidden. The horizon is the seal. The Planck star is the fossil. The relic is the storage. And the universe, on this picture, is not running down toward heat death so much as it is, slowly and patiently and across timescales longer than anything we have words for, filling up with preserved beginnings. This may not be true. We need to keep saying this. This may not be true. The loop quantum gravity picture is one of several. The Planck star is one proposal among many. String theory says something different. Asymptotic safety says something different. Other quantum gravity programs say something different again. The discipline has not yet converged. The empirical evidence is at best suggestive at the level of indirect statistical signatures, and at worst, entirely absent. The honest position is uncertain. The honest position acknowledges that we have a beautiful picture and we do not yet know if it is right. But here is what I want to leave you with. The honest position also acknowledges that the picture is, in its weirdest implications, beautiful. The picture says that every black hole in the visible universe contains, at its centre, a sealed pocket of the first instant. The picture says that the cosmos is structurally generous in a way nobody expected it to be. The picture says that the universe, in its deep design, is not the kind of place that throws things away. The universe is the kind of place that, when it builds the most destructive objects the math can describe, builds them as vaults, as archives, as long-term storage. The fossils are not accidents. The fossils are, in some sense, the point. If you are listening to this drifting towards sleep, let that be the last image. The night sky, full of stars, scattered through the disk of the Milky Way, drifting through the halo, lurking near the galactic centre, there are 40 million black holes. Each one is a vault. Each one holds, at its centre, a sealed pocket of the universe's first instant. Each one is a fossil, a small monument to the conditions from which everything else emerged. The horizons are the seals. The Planck stars inside are the contents. The relics they will become are the inheritance. You cannot see any of this. The vaults are invisible, the fossils are invisible. The relics, when they form, will be invisible too. But they are there, on this picture, all around you, in numbers that climb past anything you can hold in your head, and they will be there long after every other structure has come undone. They are the last things. They are the universe's persistent inventory. They are what the cosmos held on to when it had to let everything else go. The rescue, 3 centuries late, may finally have arrived. The rescue is not what the discipline expected. The discipline expected nature to refuse to build the worst object. The reality, on this picture, is that nature built the object and used it as a vault. The fossils are inside. The conditions of the beginning are preserved. The universe, in its deepest design, may be the kind of place that does not let its beginning be lost. The question of what is at the centre of a black hole turns, in its deepest form, into a question about what the universe is for. The classical answer is that the universe is for nothing in particular. The Planck star picture does not change that. It does not imply the universe was designed to preserve its beginning. It implies that the laws of physics, in their deepest layer, happen to have the structural property of preserving information through extreme gravitational collapse. The preservation is a consequence of the laws, not a purpose of them. But physics, in this case, has the property, and this is what is so quietly striking about the picture, of being structurally tender. The laws of nature did not have to be this way. They could have allowed every singularity to form, every black hole to evaporate completely, every piece of information that ever fell into a horizon to be permanently destroyed. The universe could have been a place that erases. It could have been a place that throws things away. It is not on this picture. It is the other thing. It is the kind of place that, when it has to let something go, finds a way to hold on. Whether that is true, we do not know. Whether we will ever know, we do not know. But the picture is there. The proposal is there. The Planck star, the relic, the fossil, the vault, the seal, the preservation, all of it is there, in the equations, in the papers, in the work of Rovelli and Vidotto and the larger loop quantum gravity community, in the careful semi-classical calculations they have done over the past decade, in the increasingly detailed 2024 update they have produced. The picture is on the table. The picture may be right. If it is right, then the night sky, on a dark night, far from city lights, is something else than it has appeared to be. The night sky is, on this picture, a graveyard of beginnings, but in the most generative possible sense. Each black hole is a fossil. Each fossil is preserved. Each preservation is, in some quiet and structural way, the universe's refusal to lose what it once was. Sleep well. The vaults are above you. The fossils are inside them. The first instant of the cosmos is, in this picture, still happening, in tiny preserved pockets, in every direction you might look. The bounce is still going on. The Planck stars are still finishing their rebound, in their own proper frame. The universe, in its deepest design, may be the kind of place that does not let its beginning be lost. That is the proposal. That is what may be true. That, in the end, is what is inside a black hole. Not a singularity, not the end of physics, a fossil, a vault, a frozen fragment of the moment everything began, held there against everything for as long as anything in the universe will last.